Hi, uh, hope you all are enjoying uh, lockdown at home and also enjoying no college days. But please don't spend no study days. ভালো করে পড়াশোনা কর, এখন প্রচুর ছুটি, মন দিয়ে পড়াশোনা কর, সবকিছু অনেকগুলো মডিউল আছে, প্রচুর সময় পেলি। যাই হোক, আহ, from the title of my video, already you have guessed what topic we are going to learn today. Yes, that is some example using residue theorem. In my last class already I have talked about the residue theorem, and you have done very few problems in residue theorems. So today we'll solve some specific problems using residue theorem so that you can understand the techniques to solve the definite integrals using residue theorem. Okay, so first we will deal with this type of problem. We can see. So in my class I have told you that if you find any trigonometric function in a main function, then you have to replace that trigonometric function by exponential I theta. Z equals to exponential I theta. You can see here. And also accordingly you have to replace all the parameters in the function like d theta and cos theta, and if you replace them you will get a quadratic equation. Okay, now to solve the quadratic equation you have to apply Sridharacharya's method. Now by applying Sridharacharya's method you will find two roots here. Now you have to be careful about the roots because you have considered a unit circle contour. Here you can see you have considered z equals to exponential I theta, right? So here r equals to 1, right? So you have considered a unit circle contour. Now, so you have to see that whether the roots are inside the circle or not. Now, only one root, that is minus 1 plus root over 1 minus epsilon square by epsilon, lies within the unit circle. Other one is not. You please verify and at your home. Now, so to calculate the residue, we have to consider only one root. Now, so here we have I have written this thing that 2 pi I residue of function z at z equals to z1, right? So to calculate residue, I think you can remember the equation here written here. Can you remember? I think so. So just I have applied the equation, and got this answer. So from this problem you have known that for these type of functions like cos theta, sin theta, you have to replace the thing uh, by z equals to exponential I theta. Okay, now we will go to the next problem. So it is function is 1 by x to the power 4 plus 1. So this type of for this type of problem you have to consider a semicircle contour. Here you can see that I have drawn a semicircle contour. So here it is 0. I have not written, I have forgotten to write. okay, and the value is extremum is minus sorry r, and at the left hand side it is minus r. Okay, now if you put the value of the r, I mean limiting value of the r, you easily can get minus infinity to infinity. Okay, so that's why we have taken this type of contour actually. So when we are considering this type of contour, so if you will have actually two integrals here. One is I for this linear part and another one is IC for this curvature. Okay, I have written here. So this equation you can write I plus IC. This is closed integral. Okay, so firstly we will calculate IC. Okay, for IC, for this type of contour, you have to deal in this way. So you have to replace x by r exponential I theta. For the previous case, what have you considered? You have considered z equals to exponential I theta. There you have considered r equals to 1. That is, you need circle contour, and you have considered the whole circle. But here you have considered the semicircle, right? Now, okay, we we go forward. Now simply I have replaced the function by uh, x equals to r exponential I theta, and we got this equation. Okay, now when you are calculating modulus, so simply you know that for a I mean complex number r e I theta, the modulus is r, right? You know well. So here simply when we are calculating modulus value, then simply we got only r values. Okay, in these equations if you consider r is very big, actually it is very big because we are giving the limiting value of r tending to infinity. So here you will get r 1 by r cube, right? So if you put now r tending to infinity, you will get 0, tending to 0 value. So we need not to consider here IC, only we will deal with I. Now, so I means that integral. Now, and other one is, and in the right hand side we will, so okay, so right hand side to calculate, I mean at the right hand side, to calculate the residues, we have to find out the poles. So here from the equation, that is x z to the power 4 plus 1 equals to 0, that is z to the power 4 equals to minus 1, we will have 4 roots. You can see here 4 roots, that those are actually poles here. So at class 2 level already you have done that. We can express minus 1 as exponential I pi plus 2 pi ki, where k is 0, 1, 2, 3, right? Now from there we will get these 4 roots. Okay, now for as we have from the previous case, we have seen the whether roots are inside that contour. So here also we have to find that which roots are inside the contour and which are not. So from the picture it is clear that only 2 roots are inside the contour, so we have to calculate residue for these 2 roots only. So I have done here, I have written, you can see that just I have applied that for equation. So you remember please that equation, just I have applied here. And you can do the problem in a other way, that if I could write the I mean that this equation as z minus z1 into z minus z2, z minus z3, and z minus z4, but I have not written because that will be very tedious job, right? So there is another simple way to solve this type of problem actually. Just write the equation, I have written the equation here. Now I will just find the thing in a simple way, right? So this is actually, if you put here z equals to 1 root, this will give 0, and also this will give 0 because it is root. So that 4 will give -1, this will 0. So I will use here L'Hospital's rules. Already you are familiar with the rules, right? So I have applied the rule and just put here. So you simply you have perform derivative, first derivative, and here also first derivative. So 4z to the power cube, just I have put the value here directly. If you do at your home, you will see the same answer. Okay, so later next I have just simplified this exponential I3 pi by 4 thing here by cos theta and sin theta, and replace their value, and you will find the final answer. Okay, so I think you will able to do this type of problem in future, and please do at your home yourself. And also you can see the examples for the first time. Now this is its next problem. Okay, this is a so I think already Kartik already taught you Fourier transform. So see here, it is looks like some Fourier transform, like, right? This looks like some Fourier transform. Okay, so we will first calculate for k greater than 0. Here k greater than 0, right? Okay, so for this type of function, we also have to consider semicircle, semicircle type contour. Okay, so naturally you know that for this contour there are two integrals, one is I plus and another is for curve one. Okay, now for and obviously I will calculate for the IC first, because it is going to be 0. You know why I am going to calculate. Okay, so you have to make it 0 actually. So how? Now see, so simply here you will replace x equals to r exponential I theta. Now you can see here, and from there you can see the exponential I k r cos theta, and minus k r sin theta. Now if I take the mod value, then simply you will get simply you will get just real parts actually. You see here, you are getting like that. Now since k is greater than 0, and if you apply the limit r tending to infinity, you will get 0 for that part. Okay, so I see 0. Now you are left with only I. Okay, so naturally I have to find the poles actually. So only there are two poles, one is plus I, another is minus I. Now simply now you will find that whether the poles are inside or outside. The one is only inside, so I have to calculate residue for I only. Now you calculate this one residue for this function, and you have applied the same rule and same formula, and you got this answer, right? Now if k is less than 0, then it is your homework. Please enjoy the lockdown, and please solve this one too. Okay, we'll go to the next problem. This is something you can see. You may think that it is something like the previous one, not previous one, the second one, right? But this is actually general problem. Okay, so you can see, if you can solve this one, you can solve by this method also, you can solve that one too. Now difference is that here the limit is only 0 to infinity. Okay, okay, let's start. So you find out first pole. What are the poles? It is a simple thing, already you have done. It is a simple thing, exponential I pi plus 2 pi pi 1 by n, p where p runs from 0 to n minus 1. Okay, now this is the little bit tricky. Now you have to select contour in such a way that just one pole is inside your contour, because it is just for your convenience. If you have to deal with one contour, why not you will do, right? It is up to you. Now you consider, for this type of case, you have to consider this conical type of contour. Okay, okay, so what is the theta actually? So here you can see that first one is I pi by n, and second pole is 3 I pi by n, right? So you are considering theta as 2 pi by n. So just one contour inside the one pole inside your contour. So for this type of contour, is one problem is that you have three integrals, right? First one is r, you can see, second one ic, and third one is I dash. So accordingly I have written those things, 0 to r, and next one is this part, you can see r is exponential I theta, just I have replaced this one. And third one is this part, and for this part you can see that this is r exponential I 2 pi by n, and then this part r. So I have written here x equals to r exponential I 2 pi by n. You can see here. uh, okay, I have replaced. So it is on the left hand side, and at the right hand side you are calculating the residue, right? So residue is just you are applying formula 2 pi I into residue of f at z equals to ei pi by n, right? So okay, now we will deal with first this curve part, because it is going to be 0. Very nice, na? All the curved, I mean, the integrals for the curved one, we are getting 0. Interesting. But you have to apply the actual logic. Okay. Otherwise, examiner will not give you marks. Please concentrate on the logics and please remember the logics. They are almost same, but there are some difference, little difference, and also tricky. Okay, so yeah, I have replaced r exponent sin theta dA theta. Okay, now it is very simple actually. Here it is simple, so it is the same way you have done before. You can see, just take a modulus and take and if you limit this one r tending to infinity, you will get 0. In the previous one you have already done. So okay, so next, here it is I am considering I. If I consider it is I, because 0 to r, and also here 0 to infinity, and here you are giving limit r tending to infinity, so it is simply you are getting this function, so you are naming it I. Okay, so you will if you see here, see here it is only the extra factor exponential I 2 pi by n. Because here you can see, if you apply, if you simplify this one, you will find exponential I 2 pi, and exponential I 2 pi is 1. If you break this one in the simple form cos theta and sin theta, you will get this as 1. So you are left with dr this one by r to the power n plus 1. So this is something like that. Something like that, just limit is in a in a different direction. Okay, so if you flip this one, so you will get this like equation. This is I minus I into this one. Right, this flip, just flip this one, and this is a residue. Yeah, okay, for the residue just apply the same thing. Just you have pole at, only pole at this one, just simply 1 by x to the power n plus 1, say, and just apply this one, and also here you use that's L'Hospital's rule, and also you will get first derivative n into this one. Okay, in the same way, just put here, I have simplified this one in this way, and you will get yes, this. Okay, more simplification needed. If you simplify more, you will find this equation. In exam, if in question, if they wants to prove or find out this equals to this, then you have to do this simplification. Otherwise, if you left with this one, this also will go, because this is also correct. Okay, this is example 4. Okay. So this is different, slightly different. This is only exponential function. Okay, so for exponential function or hyperbolic functions, you have to consider actually rectangular contours. Okay, if the function contains hyperbolic function or exponential functions, you have to consider a rectangular contour. So simply, actually, you can see here, first you try to calculate the poles. Actually, if you so it is a simple one. exponential z equals to -1 from this equation you will get, and for -1 you know we can write like this, and comparing this one you can find out z. Okay, this is I pi 3 I pi like this. Okay, now you have to draw the contour in such a way. In the previous case we have considered the contour in such a way that just one pole reside in our contour, inside our contour. In the same way, here also you have to draw the contour in such a way that just one pole reside inside your contour area. Okay, so first contour is I pi. So we will do in such a way that I pi just reside in the contour area. First one it is R. Okay. Now next part is we are considering, because it is I pi or 3 I pi. Middle is 2 pi I. So R plus 2 I pi. We are considering like that, and accordingly, if it is, since it is rectangle, so we have to choose the boundaries in the same way. Okay, so just you have to calculate residue for this just I pi. Okay, now for this cross integral you have 1 2 3 4 integrals, right? So first one is this one I've written. See here, it is a simple thing. Just you can see that just it is a same thing for here. Okay, this is I, and this is going to be I actually. And second one is for this one. For this one you have to write this in a uh, uh, tricky way. So this is y-axis, right? If this is x, this is y, and you can see always there is r, and just you are varying in to this part 2 pi I. Okay, if you write here, you can, if you can see IY, if you consider IY, then simply if you put 2 pi here, you will get this one. Okay, R plus 2 pi I. So that's why we are considering here R plus IY. Okay. So y equals to 0 to 2 pi I dy. You need not write y equals to, actually if you write 0, because you are performing integration on y. Okay, here I've written this one, and for that part it is just shifted. Shifted uh, uh, from here to here by 2 pi I. So 2 pi I should be constant. Then it is constant, and x is varying here. So R2 minus R, here R2 minus R. Okay, limit will be R2 minus R. Yeah. And for this part, just the same thing, just limit and R will be different. Here R will be minus R, and limit will be 2 pi to 0. Okay. And for the residue one, 2 pi, if you calculate residue, simply you have to apply same formula, and then you have to apply L'Hospital's rules. Okay, so just you will have the same thing. Okay, so okay, next. So first we will deal with this one. Okay, so I have written here, you can see, taken mode of this one. If you take mode of this one first, since r is tending to infinity, so I mean very big number, so you can replace just this one by 1 plus exponential r plus iy by exponential r plus iy, right? You can write, and then here, since you are taking modulus, so just you will deal with the real parts actually. So simplifying, you will get 1 a minus 1 into r. Now here it is written a is in the limit of 0 to 1. Okay, so a is less than 1, that means this is negative, this is negative. So if you put the limit r tending to infinity, so it is going to be 0, right? Because exponential minus r something, minus r, that means 1 by exponential r, so that is giving 0. Now in a similar way, it will also give 0. So you don't need to consider these two, and just you will consider these two terms. Okay, so these two terms already I have told, this is this will looks like I, this same function. If you can write this as I, and also this one, just if you flip this one minus, and just there is a extra factor, right? Exponential 2 pi I a. If you write this one and simplify, and already you have found this one, I mean residue here. You can see and exponential I pi is minus 1, so you have written minus 2 pi I exponential a pi. Then just simplify this one, just put here and multiplied by this one, and got this answer. Okay, so this is done actually. Thank you for your concentration, and I will try to upload more videos in another topic. Okay, so I think it may be probability. So uh, please stay at home, and please read all those things, and enjoy at your home. Simultaneously, please don't waste your time. Please read carefully. Thank you. Bye.